Hello everyone, my name is Michał Wilczyński. I work as a kernel engineer for Samsung Electronics. So my area of work is TizenOS. It's an OS that's running on Samsung smart TVs. It's obviously Linux-based. And today I'm going to be talking how I leverage the eBPF to make this system work faster and better. So we're going to focus on two deep dives. The first one would be a low memory monitor using eBPF, and the second one would be a dynamic cache tuner. It's also using eBPF to make decisions. To give you some roadmap where we're going, first I'm going to talk about the challenge. What's the challenge with resource management on the embedded systems? In this particular presentation, I focus mostly on the memory. And then we'll talk about the architectural approach, how the eBPF was used for observability, and the user space daemon was used to actually make things happen, make decisions based on the data that was extracted from the kernel using eBPF. And as I stated in the previous slide, deep dives into the first solution, the proactive low memory monitor, and the second, the dynamic I/O cache tuner. I will show the eBPF code, benchmark results, and some conclusions at the end. So let's start with the core challenge. For example, let's think about this Samsung TV that's running TizenOS. It's not just a single workload. It has to run, for example, Netflix. It has to run a complex UI. So the problem with the current approach and the Linux kernel that it has some defaults that are one size fits all. So, if workload demand exceeds this static configuration, then you may end up with a performance bottleneck. And so this seesaw diagram is something that illustrates one of the trade-offs in the kernel that is controlled by the VM dirty ratio parameter. So by controlling this parameter, you can assign more memory for cache, and then you will get a faster I/O. But obviously, conversely, you will get less memory for your apps. So depending on the workload, the value of this parameter might be the optimal value of this parameter might be different. So that's the challenge. We need to observe the kernel and decide based on what we observed. What's the optimal value of this parameter, for example? So how do we solve this? So this is the high-level architecture. So basically, I decided to use the eBPF programs only for observing how the kernel works. So we're going to be attaching to some K-probes and trace points in the memory management subsystem in the block I/O layer. This, data will get sent to the. This is actually a TizenOS specific daemon resource D. Typically, in other distributions, stuff like that would be handled by systemd, I suppose, but we use resource D. So then the resource D makes decisions based on observed data. So first, I would like to give you some background on something that's called PSI. This is, I think this has been for a long time in the kernel. This is pressure stall information. So this is a subsystem that gives you information about how much time tasks are being stalled waiting for CPU, memory, or I/O. And it gives you this data by three decaying windows, decaying average windows, 10 seconds, 60 seconds, and 300 seconds. So basically there is some lag. There is also a possibility to just pull the total number of microseconds that tasks are being stalled, but this is not what the current solution used. Current solution for detecting low memory scenario. So if you have that many tasks waiting for memory for that long, then this is, you're basically long overdue to take some action. So what would be the solution? So the current approach for detecting low memory scenario is just using the PSI and the thresholds. For example, if you have like 30% of tasks waiting for memory, that this means then the system is in a state of memory pressure. But we can actually do better. We can do better by using eBPF. So we can use different signals from the kernel to not only have the symptom, but have a leading indicator that the memory pressure situation is going to happen before it happens. So one of the leading indicators, for example, K-swapd wakes. K-swapd is like a kernel housekeeper of memory, and a higher frequency of K-swapd wakes means that maybe potentially there is going to be a problem. And the other indicator is fallback alloc. So the kernel, when it's trying to allocate the memory, it first takes a fast path. But if it can't do that, then it tries the slower path. So this basically means that there is still memory, but it's not as easily accessible. So if this starts to increase a lot, then this means that there is probably going to be a problem. So the more severe indicator would be a direct reclaim. So direct reclaim basically means that there is no memory, so the kernel has to do the work and try to reclaim it from somewhere. For example, by writing back some pages to the I/O. So yeah, that's what we can do. That's what we can observe. So here is an example of the map that we use to talk to the user space, and code for the eBPF probe to the specific trace point. It's called VM scan direct reclaim begin. So this is basically counting the occurrences where this function is being called. So the more it's getting called, the more direct reclaims happens, and the more we can say that there is a memory pressure situation on the system. It's obviously using helper to add to do this atomically, because yeah, we have to do that. Okay, so what is the problem with these counters? So the problem with these counters is that they can be very spiky. So we have to do something to smooth them. So one thing that we can do is we can use exponential moving average. So this is a moving average that's used a lot in the financial markets, for example, because it's like shown on a plot. It can smooth out the noise and react very quickly to trends. And the one very important thing about it is that it doesn't really use almost any memory, and it's very easy to compute, as shown in the formula. And for the eBPF observability, this is a requirement, basically, because we can't be using a lot of memory and a lot of CPU cycles. So this is something that I chose to do this smoothing. Okay, so now we have the data collected. We know the background about the EMA. So what does the resource daemon or the user space part does? So it basically pulls them up every half second, uses the EMA described in the previous slide, and then basically applies the hybrid trigger logic. So if there is a sudden spike, even after smoothed by the EMA, it raises the memory event. or if there is an extended pressure, then they just raises low memory events constantly. So one nice thing about choosing this particular feature was that a lot of stuff was already coded in the user space. This was like our pilot feature. So we could see whether we could actually use eBPF in this way. So we just exchange the part that is doing the observability with PSI, with the one that's using eBPF. So we can check it and benchmark it very well against the previous solution. So a lot of code is common, only the BPF observability part is different. So we can basically say this is that much better, right? Because it's taking the same actions when the low memory situation happens. So this is what it actually can do. So it can put some processes in the C group freezer, send system-wide warnings. There is a custom out-of-memory handler in user space. As a detour, maybe if someone is watching the kernel mailing list, there was a proposal recently to do an out-of-memory handler in the kernel in eBPF, like a custom one. It doesn't. You can't do that currently. It was proposed earlier this year, and I think the patches are still alive. So one thing we really care about is with the custom low memory killer is that we won't kill the wrong processes. We really care about the processes that the user is interacting with. So we need to protect them. That's why there is a custom one. We have them in separate C groups. So in case there is a high pressure on the system, we protect the processes that the user interact with, so the user experience is as best as possible. Hey, so let's see the benchmark. So as I said, the top one, this is actually the eBPF one. So I guess this requires some explanation, because this one goes very up and down very quickly. But in general, this is a desired behavior, because what we want to do is we want to allow the processes that need memory to be able to allocate memory. So this is actually, since the benchmark was very aggressive, I used stress-ng with many workers, and they all want to allocate memory. So the eBPF monitor is actually picking up this very quickly, and is invoking the low memory killer and so on. But in general, this is what we want, because we want to regulate system. We don't want to, like on the second graph, that there was like a saturation. So many processes that wanted to allocate memory couldn't allocate memory because the signal wasn't there to, that there is an imminent low memory situation. So in the first graph, we actually protected the things that mattered. And on the second one, we didn't, because the memory was saturated, and maybe some user-facing process couldn't allocate the memory that it really needed. Okay, so we're done with the first solution. This was something that I described as plug and play. So because the observability part was exchanged for the ease of benchmarking. So this is something harder. In here, basically, we are trying to modify the VM dirty ratio parameter. And to explain what this is, I mean, when the Linux kernel is trying to write to a file, it first writes it to something that's called page cache to feel instantaneous. This is a memory buffer, and this parameter basically describes how much memory percentage-wise the kernel can use for the page cache. So this is typically a static, some default in the kernel. This is a CTL. But in general, if we increase it, we will get a better I/O performance. But if we lower it, then we will have more memory for our applications. Okay, so we want to observe the kernel and see whether we should be increasing this parameter or whether we should be decreasing that. So one way we could extract some signal from the kernel is by measuring how long the memory reclaim takes. So if it's taking a very long time, that this is probably a very bad idea to increase, for example, the VM dirty ratio, because then you will have a lag. You can actually measure that lag because one of the ways the kernel can reclaim the memory is just writing back the pages, right? So here you can see the BPF program or programs that attaches to the two trace points. There is one trace point when the direct reclaim begins, and there is one trace point when it ends. So we can basically do some sampling as well. Well, in my testing, it wasn't really that necessary. I was testing on Raspberry Pi, so it was about 1 in 4 there. And then there is a per CPU map. We calculate the timestamp at the end, and then see in the end probe whether the start was sampled, and if it was, then we calculate the delta and put it in a map basically. So that was an easy one. So the hard one is, for example, measuring the I/O latency. The problem with block start request function is that this is an asynchronous operation. So and the other problem is that the block update request, this can be a partial end. So this can still not. So the sole fact that this function was called, it doesn't mean that the request was completed. We only know it when we have the return value of this function. So we only know it actually in a k-ret probe. So that's why this has to use 3-probe, 2-map solution. So in the first one, we basically store the pointer, request pointer, and the timestamp. In the second one, we store the process ID and the request mapping. And in the k-ret probe, where we can actually access the return value and we know whether this was a final request, we can decide whether. Actually, I do have a code for that function, so we can go through it. So in here we see whether there are any more bytes to process. If there aren't, and this is a final request, then we get a calls map. This is a bridge map, and then we can actually access the request pointer. And having the request pointer, we can access the original timestamp. And with that original timestamp, we can calculate the delta. How long does it take to reclaim memory, basically? Okay, so before we get into the user space part and the benchmark, I wanted to talk about how this is the architecture, how this is structured. So I wanted the architecture to be extensible. So in this particular tuner, we're just tuning the dirty ratio parameter, but potentially there would be more tuners. So it's with the way I coded it, it's very easy to add them, because all you have to do is just fulfill the contract, the struct sysctl tuner ops, provide init function, exit function, and update function. So the init and exit would probably be just loading BPF programs, and then the background thread would update through all of them periodically and update them. So you just have to call the macro, fulfill the function, and that's it, basically. So I wanted to make it easy to add more parameters. Okay, so we have our data that's coming from the eBPF, that's the memory reclaim latency or I/O latency. So the idea here, and I'm sorry if the text is too small, I was trying to make it bigger. So I will just talk about it. So at the top there's the data sources, on the left, the one I mentioned on the previous slides. So the latencies. On the right, there is actually a PSI. Because to make this very robust, I've thought that we need to have multiple data sources. So then, this go into the 1 minute rolling average, because we don't want to respond to some brief spikes. There needs to be some extended memory pressure or extended I/O pressure, and there is some cooldown. For 60 seconds, I decided on that value to be just conservative and not to do any flapping. So if, on this 60 seconds average, it is decided that there is a high I/O pressure and low memory pressure, then we increase the VM dirty ratio. If it's the reverse, there's high memory and low I/O, then we decrease that. If there is really no pressure, then we don't really do anything. So, yeah. All right, so what are the benchmark results? So I created some benchmark using StressNG that was doing some random memory, random disk writes, and with some memory pressure. And with the tuner, it actually ran much quicker. It actually completed 15% faster. So yeah, I think the use case is there to tune the system to the specific workload. Okay, so what are the conclusion and key takeaways from this presentation? So, based on my experiments, it seemed like using eBPF for this kind of thing, when you observe what's happening in the kernel and building resource management or software that is moving some parameters, this is a good idea. Because you have a eBPF verifier, and you can basically write some code and be sure that it won't break your kernel while you're still getting information that is useful. The low memory monitor, it actually worked pretty well. It was able to detect imminent memory pressure situation much faster. Yeah, the same for the dynamic cache tuner. And the architectural design pattern using eBPF only for the kernel part and using the decision making is actually really cool for the iterative development, because a lot of software in embedded, it's actually there. So it's best if we can do something like plug and play. Include the eBPF for observability and use the existing software for making actual decisions. I've uploaded the code for GitHub if anyone is interested in looking at the actual code. This is a fork of the resource repository from Gerrit. It is open source, but on Gerrit you have to actually create an account, I think. So that's why I forked it. So it's easier, right? Who would create an account? So, yeah. Okay, so thank you very much, everyone. I would be very happy to take any question, if there are any questions. Okay, who was first? Krzysztof?
So the benchmark was on the Raspberry Pi?
Yes.
Did you try benchmarks on some x86 platform, some more cores, 8 core?
Well, I don't work for an x86 company. Huh? So, yeah, so Raspberry Pi is one of the reference targets for the TizenOS. It's very well supported, so this is a good choice, I suppose. Obviously, when running on Samsung TVs, there will be Samsung-specific hardware. Who else? I think you, right?
Yeah. So I have a question about the exponential coefficient that you have in your EMA, the alpha.
Yeah.
How did you choose that?
So alpha is there's a formula for alpha, with when the input is n, which means period, basically. So you basically choose it based on how long ago you would like to peak, in a way. So yeah. So I chose some a value at random at first and then benchmarked in to get the best result. All right, here.
You pull the data each half second. Do you pull it from shared memory, or do you store lots of data in with the eBPF program and then pull everything
So-
in memory, or?
It's not shared memory. There's a construct designed for eBPFs.
The part lengths, or?
No, it's a eBPF map. That's what it's called.
Okay, you read out the map, so it's basically shared memory. Yeah.
In some sense, yes.
And do you have different pull times for different tuners, and how do you tune the pull time?
Well, there is one tuner for now. So yeah. So hopefully there will be more. For now, I chose the values based on how I observe the system and to get the best result. So I assume for different tuners there would be different optimal values for polling, right? And depending on the system as well. Okay.
My question is kind of a continuation of his. Why did you set on like using per CPU maps instead of something like a ring buff? Because essentially you're acquiring a spin lock every 500 milliseconds.
No, I'm not doing that. I mean, with EB,
If you bought a map by reading it from user space every 500 milliseconds, you are acquiring a spin lock because you can't update it from kernel space. And you have like all of the things you export are fixed size, right? So you can just reserve a ring buff space from all threads. You don't have to parallelize that.
okay, maybe that would be an improvement, right? But still, every 500 milliseconds, this is not that much, even if I was taking a spin lock, right?
Yeah, it depends on how much events you have, but yeah.
Yeah. Okay, please.
You've showed us a few programs. Are there more programs involved in your tooling? My second question would be then, is there any noticeable CPU overhead when you run all those programs, or is it non-existent in your use case?
So there are more. That were an examples. I tried to measure that, but the performance wasn't very. I would rather worry about maybe the scheduler or because obviously those threads needs to be scheduled that would run the eBPF program. So maybe there would be some problem here, but I don't have the raw numbers. I wanted to do that eventually to see how much overhead there is. And I think that would be a great, project to do, but I haven't got time yet to get all the raw numbers. Yeah, it's a very interesting question there. Any more questions? Okay, please.
How frequent do you think this method would be able to pull and react to events? Do you envision going from 500 milliseconds to 110? Or 1 millisecond with the scale?
How much quicker?
Can you envision any use case where you'd want faster polling, and will this method scale to that?
Yeah, so this is a trade-off as well. So basically lowering the polling will give you much faster response time, but then you will have much more overhead. So I can envision a use case where it would be useful to have lower polling time. But I guess this one is not it, at least not in my testing. Yeah. Anyone else? Okay, thank you very much then.